Hello, everyone. This is the lecture for section 2.3, volumes of revolution, cylindrical shells. So this method is the harder one of the three methods to find uh, sort of a volume, okay? Um, the theory is just about as simple, except there is a little bit of a modification here and there. Uh, Okay. And it has to do with cylindrical shells this time. Okay. So let me build up with the theory just using our basic geometry, right? And then we'll build up to the more complex stuff and how it turns into an integral. Okay. Um, the idea for how we build our integral is just the same as when we did washer method and disk method. The only difference is we're doing cylindrical shells. So the one thing that we're going to need um, is well, let's first start with just the basic geometry that we're going to need. Okay. Um, as the method suggests, we're going to be using cylindrical shells. So picture sort of soda cans. Okay. And we're going to be making soda cans that sort of start out really small and grow to something really big, right? We add up all of those soda cans together and we get a volume. Okay. That's sort of, really quick, the idea, right? But now let's build up the theory. So the one geometry rule that we're going to need, right, is it's not going to be this one, but it's going to be the build up for it. So if we want the volume of, let's say, a nice little slab like this, right, then the volume of this thing, whoa, wrong color. And the volume of this thing, right, is going to be some length, right, times some height times a little, if you guys take a look right here, it's going to be a little sort of width or a depth, right? So it's going to be a length times a height times a width, that little piece right here, basically the thickness, right? Now, picture this, if you will, right? Suppose you grabbed this end, this entire end right here, right? Spun it around and stuck it to this other end over here, okay? Then you have a cylinder, something like, looks like this right here, right? So what ends up happening now, right, is our width, right, our width right here, right, is going to be that thickness. It's going to be the thickness of the our cylindrical shell, right? The height, so basically from sort of right here all the way down till we get to the base right here, that's still going to be our h, right? That's going to be our little h. And actually, let me call it big H because that's what we were doing before, right? And since we're looping it sort of in a circle, right, the length now, we need this thing right here. It's going to be some radius r, right? So the volume here, right, turns into 2 pi r. That is going to take care of this length right here, the length that goes all the way around, right? Times our height, times our height, times our width, right? So this is the volume of a cylindrical shell, right? Just one, right? Just one that we just sort of take out separately, all right? So this is the theory that we're going to end up using here, okay? So now, how does this fit for finding our volumes? So let me go down here. There's a blank space here now. Please give, don't judge me. I think I've mentioned this multiple times now. One of the things that you learn to do in Calc 2 is you learn how to draw, and you learn how to draw really good. Um, I am on an online, I'm on like on my desktop computer, so my lines may not be exactly perfect. I'm trying, okay? I'm trying, there we go. All right, so I'm slap down an X and a Y. I'm gonna label which ones I'm gonna consider X and which ones I'm considering Y. Okay, so this is gonna be my X variable, right? And this is gonna be my Y variable. So your XY plane is sort of like the one that's standing up, right? And I'm adding this third axis here just so that I can give sort of like a depth, okay? Okay, now here comes the construction. Okay, suppose, right, we have a continuous f of x, non-negative, over an interval ab, right? So I'm going to go ahead and draw I'm going to draw my function here. Okay, I'm going to do it in purple. I'm going to go ahead and do, there we go. Okay, and I want it between some value a and some value b. Okay, so then that means on the other side, over here on my x-axis, the negative x-axis, there's going to be a negative a, there's going to be a negative b. These aren't going to be too useful for us. It's just to show where they end up going. So then here's my a, or here's my f of x. Okay, so this is f of x right here. Okay, and suppose we do a partition, right? So I can still grab my AB here and sort of partition them up, right? Let me do that one a little. Let's go and there we go. Okay. And in this case, right, let's say we want to revolve this shape about the y-axis. So we are trying to spin this like this around here. Okay, we're trying to spin it around the y-axis. So let me go ahead and sort of cordon off let me, that's a bit too thick. Bear with me here. Bear with me. I'm trying to be as precise as possible. Let me zoom in really quick so I can be a little bit more precise there. So I'm trying to cordon off this thing right here. So this is the shape that I want to revolve around the y-axis. Okay, so let me redraw this strip right here so that it looks a little better. It's going to go something like that, right? So I want to revolve that shape around, right? So I'm going to use my blue again. Don't judge me. Don't judge me. Please don't judge me. And I want you guys to see the shape that's going to sort of take shape here. Whoa. I was doing a, oh no. Thank goodness for undo. Too much. There we go. Hopefully, let me do this bottom end really quick. Hopefully you see the shape that's there, right? I know it's really hard to see it, but let me see if I can highlight it with a nice dark blue here. Too big. Let's go ahead and make that a little tinier there. There we go. Maybe let's go. Yeah. Basically this shape right here. Hopefully you guys see what's going on here. Let's shade that thing in right there. There we go. So you have this little, it looks like a sharply edged donut, right? With that hole in the middle, right? And that's sort of on purpose, okay? This is the shape that we want the integral for. This is the shape that we want the integral for, okay? This is the volume. This is sort of like the shape that we're going to be looking at, right? So now let me go ahead and delete the filling in so we can do a little bit more calculus now. Not what I wanted. Now we'll have to leave that there. Okay. So what I want everybody to see now is this. Let me actually get rid of the shape really, because what I really want to concentrate on is the cylindrical shell that's going to be used, right? So the cylindrical shell that we're going to be using, right, is this one. I'm going to take a random one because we can go ahead and do that just for sort of illustrative purposes, right? Here's our cylindrical shell. There's a, right? And then, so same thing's going to happen on this side. There's going to be a, a slice that's missing there, right? And I'm gonna go ahead and try to connect these dots like this. That's the inside one. This is the outside one, right? The outside one here, and then the outside or the inside one here, like this, right? And there's a height there, and I'm gonna go ahead and outsides to insides. There we go. So hopefully you guys see. Let me see if I can draw it a little better so it actually looks like a cylinder. So that's going to stay there. I'm going to dot this line instead. Okay. Hopefully you guys see what's going on here. And then let me do this one here on the outsides. And there we are. Let me dot that one to show that's the inside. There we go. Okay. I think that's going to be the best thing I'm going to be able to do. Okay. Hopefully you guys, now I'm going to actually shade in what the cylinder is going to look like. And I'm going to try to do it so that it shows sort of like a cylindery shape, if that makes any sense. So that's the outer lip. If you take a look at a soda can, right? That's the outside outer lip. Okay. And then the rest of it, right? All this, all the way down is sort of like the rest of the can. Hopefully this makes sense. Hopefully the picture is clear enough. I really hope the picture is clear enough. If you need more sort of if you need a better illustration, I know the book has a pretty darn good one, right? So here's our sort of cylinder that we're going to be playing with, right? We're going to have a bunch of these cylinders, right? They're concentric cylinders, so they start off small and go big, or big go small, right? They're just sort of cylinders inside of cylinders, right? We're going to grab the volume of all of these cylinders, add them up. That's going to be our volume, okay? So the anatomy of one of these cylinders, right? Hopefully you guys can see how this is going to work out. Let me go ahead and use the pink here. We know that this width, this little strip right here, is going to be our delta X because it's part of a partition, right? It's going to be a specific width, right? Okay. We can tell that there's a height here, right? That height is going to be dictated by f of x I star, right? It's going to be dictated by some x value that's within this partition right here, right? Okay, and then the last thing that's left is we need a radius, and we can tell that this radius this way, right? That radius right there is going to be, and I'm going to sort of do this right here. There we go. Is going to be the r there, right? Is going to be whatever that x value is, right? Some x of I. And actually, I should have done it the other way. Let me back up here. Let's go ahead and do it this way so we can get to this point right here. So this right here, whoa, this radius right here, r, is going to be given by xi star, some x value within that one partition that we're choosing out, right? That's going to get us our cylinder. So the volume of this cylinder, the blue one in particular, right? The volume of this cylinder is going to be given by 2 pi xi star times f of xi star times delta x. Okay, hopefully you guys see that. Like I said, if you need a better illustration of it, I highly suggest you go to the textbook. I'm trying my best here. Okay. So that's where this term comes from, right here. Okay. And as we did in previous sections, right? If we grab all of these f of x, v of xi's, right? If we grab all of these smaller volumes of all of these cylindrical shells and then just add them all up, we get our volume. We get the entire volume of the shape. Okay. The next thing that was left after that, which was what we've been doing sort of since the beginning of the semester, right, when we started learning about integrals, is if we make those little partitions, if we make these partitions down here, we make those partitions smaller and smaller and smaller, right? Then we get a better and better approximation of our of the volume of the shape. Okay, and when we do that, we get our integral. Okay, so if you guys take a notice right here, right, that's still the expression for one cylinder, right? I'm adding them all up, right, from I equal 1 to n, so there's going to be n different partitions, right? And then I take the limit as n goes to infinity. The second we take the limit as n goes to infinity, that turns our thing into an integral. Okay, and notice how the shape, notice how the formulation of the integrand is still the same sort of as the formulation for our volume, right? This little strip right here. So this, right, all of that ends up being all of this. Okay, awesome. All right, so now, how do we freaking do this for real, right? Let's go ahead and take an example, okay? So this one, a big apology here. I forgot a negative. So there should be a negative after the before the 5x, x minus 1, x plus 1. So just make sure you stick the negative in there, okay? Suppose we want to find the solid of revolution, right? Formed by the revolving the region bounded by that thing over 0, 1 about the y-axis. So we want to spin this way. So we want to grab this shape. We know this is the region that we really care about. We want this region right here, highlighted in pink actually. We want this region, all of this, right? All of it. And we want to spin it around the y-axis. So we want to do this. Okay. Okay. So let's get that started now, right? So what I'm going to do, and I hope, and I expect everybody, when you guys do this for the quick checks, you at least attempt. Okay. I'm not judging, this is an art class. I'm not judging your picture, right? But I do want it to demonstrate all the important parts. Okay. What I want to start with first with this problem is I want to draw the shape. I want to be able to at least somehow, slap down a visual representation of what I'm going to be playing with. Okay. So I'm going to go ahead and do exactly that. Let me go ahead and I'm going to do a shape. I'm going to draw an X and a Y axis here so that and we didn't want it in pink. There we go. I'm going to put another one down. I'm going to put it maybe like that. There we go. Okay, so that's just X and Y axis, right? Just so that I can get my bearings down, right? I'm going to extend this one a little bit. Oh, come on. There we go. Okay, and I'm going to make the, not what I wanted. Come on. There we go. Okay, so I have my X and Y axis down, right? And what I'm going to do, and I'm going to zoom in a little bit. I know what the shape is going to be. I know this is the shape that I want, right? So I'm going to go ahead and do 0 to 1. I'm going to put negative one out here just as a reference, just so that I know what's going on, right? And I'm actually going to put it a little closer right there. That's cool. Okay. And I'm going to draw the region sort of. I'm going to draw it in blue for now. So I know this thing is going to go like this, and then it's going to drop down like, whoa, almost so close. Up, like that, and then there's going to be a dip like that. There we go. I'm going to do the same thing over here. It's going to go up, and there's going to be a dip. Whoa. Like I said, I'm trying to draw it as best as possible so you guys can see what the shape is supposed to be, right? Attempt your best to draw the shape as close as possible. There we go. I think that'll do. Okay. And I want to revolve this around the Y axis, right? So like I said, I want to spin this way. It's going to go like this, right? Now, here's the shape. I'm going to go ahead and sort of connect the tops. Oops, wrong button. I wanted the undo. There we go. I'm going to connect the tops a little bit like this. And then the bottoms like this. And then something like that. So if you take a look at it, right, the shape that we are sort of playing around with here, I'm actually going to draw it in, highlight it in blue, right, is all of this. Picture like a mound of dirt, right? And you sort of scoop out the middle. You sort of scoop out the hump in the middle, right? Best sort of description I can give you. You have this cone little shape like inside, right? And that's supposed to be sort of like empty, right? Okay, so we have our shape. This is the thing that we are going to be finding the volume for, right? So now what I'm going to do is I'm going to sort of demonstrate the one cylinder that we're going to be sort of concentrating on, right? So I'm going to go ahead and I'm going to draw this a little thick. I'm going to go ahead and draw it thick so that you guys can see what the cylinder is going to look like. I'm going to make it like about right here. There we go. Yeah, that sounds good. So our cylinder, actually I should have done it a different color. Let's do it this bright pink. We can all see it. There we go. So here's our cylinder, right? Well, at least those are our sides, right? Let's go ahead and draw what the cylinder is sort of going to look like. Our soda can. It's going to be sort of like this, right? Hopefully you guys see what this is looking like. There we go. There's our soda can. Okay. There's a couple of things that I want to point out. You guys see, there's a reason why I drew this a little thick, right? The thickness that I gave this thing, right, this soda can, this is going to be our dx. Okay. That's going to be our dx. We can see that this thing has a height. So this height right here, right? That's going to be our height. And if you can tell from the other side, right, this is also going to be the same height. The height is dictated by our function. It's going to be dictated by our function f of x, right? And the last thing that's missing is basically our radius, the distance from here out, right? And that is dictated, our radius is going to be x, right? So notice how the construction works when we draw these things, right? Whoa, there we go. Notice how the construction works when we draw these, okay? It really helps out to draw it and be able to sort of slap down what your cylinder is supposed to look like as close as possible. This is one of the spots in calculus 2, at least, where you really want to be meticulous, okay? It doesn't got to be perfect, but make it as clear as possible, at least for, each one of you. Don't try to cut corners on the picture itself. Try to be as precise as possible, okay? Because the preciseness will help you properly write down what you need to for the function itself, for the integral itself, okay? Okay, so we have everything we want here, right? So in order to find this volume, right, we need the integral. Let me draw a smaller integral. The integral, we know it's from 0 to 1, okay, of 2 pi times x, which is cool, right, times our f of x. This is where we got to do our minus 5x x minus 1, x plus 1, dx. So this is the integral we need to find. And that's a multiplication before people get confused. There we go. Okay, I'm going to reduce this a little bit. Integral. What am I going to reduce? There's a 2 pi. That's a constant. I can pop that out. And there's a minus 5 times all the rest of the stuff. That's also a constant. I can pop that out. So what's going to pop out now is negative 10 pi times the integral from 0 to 1. And all of this stuff, the x, another x, let me actually underline them. The x here, x minus 1, x plus 1, that reduces down to x squared minus 1, dx. Okay, and if you expand this, get something nice. Whoops, forgot the negative 10 pi. Integral from 0 to 1 of x to the 4th minus x squared dx. That we can integrate, right? And when you integrate it, you get minus 10 pi x to the 5th over 5 minus x to the 3rd over 3, evaluated at 0 to 1. Okay, if you do the math out here, negative 10 pi 2 over 15 if you do the common denominators and everything for this thing. And what you reduce down to is 4 pi over 3. And we are done. This is our final answer. If we go through all the work and do all the arithmetic outright, this is what we get. Okay. Our integral calculator still works here, which is what I want to do. I want to bring this down and show you guys the integral. So let me go ahead and erase that, delete all that stuff. We're about to get to that one in a second. I want to do a split screen here. So we wanted to find this integral right here. I can put in any one of them. So I'm going to go ahead and put in the minus 10 pi x to the 4th minus x squared, right? So we're finding that integral. So basically we're doing this one right here. Let me highlight the one that I'm sort of concerning myself with here. This one right here. That's the one that we're taking care of. And we need it from 0 to 1, 0 to 1, 4.1887, right? And if you compute that, if you actually compute 4 pi divided by 3, this is it. Okay? So you can double check your work still with the definite integral calculator if you need it. Okay? All right, what's coming up first for everybody is your first quick checks. There's a reason why this one's the most complicated one. It's because everybody gets lost. When you're doing your quick check, let me put all of them here. When you're doing your quick check, like I said, be meticulous as you possibly can, be as exact as you possibly can, okay? The better you do it now, right? The better it'll get, you know, you'll improve your picture over the semester, right? And hopefully by the end of the semester, right, you'll be able to draw them pretty nicely, okay? They will help you formulate the integral properly, okay? So as I did in the example before, make sure you give me the region, then attempt to draw the shape somehow, right? And then give me the mathematics for it after that. Okay? Cool. Moving on, I want to keep going here. Okay. Whoa. Let me scroll down. There we go. Moving on. Just like we had integrals that were based on dx when we were doing the x-axis, right? We also have a formulation for the exact same thing when we want to do it over the y-axis, over the y variable, right? The theory doesn't change, right? So notice how this is still the same as from when we did it with the x, right? We add up all the soda cans together, right? And all of them collectively become an approximation for our volume, right? And the second we start making those partitions infinitely small, we have a integral. So notice how the integral for when we do it with respect to y, right, is the same. It's exactly the same. Okay. Okay. So up until now, we have three different methods to do to find volumes. Two of them we did in the last section, and now we're covering the very last one, the shell method. Okay. So what I want to do is sort of show how each one of these shapes look like and how they work. Okay, so I'm going to go ahead and slap down a X and a Y here. And I want it in, come on. I think it's, okay, let's erase you again. Shape, I'm going to slap down an X. I'm going to slap down, and I'm actually going to do an X over here, right? Let me move it off there for a little bit. There we go. And a Y. Okay, so the first one was a disk method, right? The disk method dealt with just any shape, right? Oops, there we go. The shell method had to do with just any shape. So I can have a function, right? And let's say I wanted to do it from A to B, right? So my shape was going to be this thing, right? This sort of wonky looking cylinder thing, right? So it was going to go all the way down to the same amount. And let me actually do that down here. Don't judge me. Don't judge me. Right? So this is the shape. This is the sort of the region that we were going to revolve around the x-axis, right? Okay. So our shape for this was actually going to look like this. It's going to be I don't know what you would call this, just like a cylindrical blob, really. Right? So I'm trying here. There we go. That's better. Here's our cylindrical blob, right? And the idea was we were doing it by disk method, right? There was going to be a disk. There's going to be a disk in between here. There's going to be a little sort of a delta X, and then we were going to basically a frisbee in the middle, right? Where we were doing it based off of this area, if you guys remember, right? This area right here, right? It was the pi times r squared, right? And that r was dictated by our function f of x, right? So this ended up being pi times f of x squared, right? And our depth, right, the little thickness here, that right there was going to be our dx, right? What's dx? dx, which ended up being our delta x, right? That's how we constructed this volume, right? So similarly, when we did washer method, the washer method was mostly for stuff that had a hole in it, right? So I'm going to slap down another x and another y axis here. Okay, so we had this time, right? So here's f of x, here's a line, right? So I'm going to do another line right here. And my squiggle, don't judge me, don't judge me. I'm trying here. A to B, right? We were going to revolve this strip right here. Let me drop that down there. So the little strip that we're going to do now is that bit right there, right? We're going to revolve that around, I'm going to do the same thing down below. I'm going to sort of dot, 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 dot down here, dot, 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 dot down there. We can see our shape coming to form here, right? Excuse me. You guys see this shape coming to form. Whoa. Oh, it went into shape. Okay. Try your best. Try your best. I'm not gonna. I do want to see an attempt, though. I will say that. I do want to see an attempt. Okay. And this is going to be sort of like inside, and this is going to be another inside, and then there's going to be the outside that goes on. There we go. You guys hopefully see this shape. It's basically the same looking blob from our disk method, right? It's just got a hole through it. Okay. If you remember this one, right? The tall one, the big radius, was our f of x, right? And then the small little radius was our g of x, right? The idea, right, is we still needed this, and I'm going to draw sort of like a washer inside with the missing hole. Hopefully you guys see what's going on. And then I'm going to add that thickness there. There we go. That looks pretty good, huh? Okay. So remember that thickness, right, is still going to be our dx, which is, back from our construction was our delta x. It's going to be a thickness for our washer, correct? Okay. That thickness was going to be multiplied by, if you guys take a look, there's, hopefully I can do this. Let me do blue. Yeah, there we go. Just trying to shade in the sort of the face of my washer, if you guys see what I'm doing here. It's my face of my washer there. Yeah? Okay. And the way that that was going to translate, right? We still needed, just like we did before, we needed an area here, right? And the way that we sort of constructed it was going to be a pi. Let me do it a little smaller here. So the area for that strip was going to be some pi times some big R squared minus some little r squared, right? And it turned out, let me move this out of the way, because of how everything was assigned, right? Pi, it's going to be the big function. If you take a look at basically from here up, right? That is f of x. And then from middle to the sort of inside radius, that's g of x. So we had here f of x squared minus g of x squared. That was our area, right? So that's how we got this formulation right here, right above it, right? Just like we got from the disk method, right? Hopefully you guys see that, right? So now, shell method. This one's the one that feels a little complicated, and for good reason, it is. So let me go ahead and draw again. I'm going to insert same idea. No, not that. One day that will be useful, but not today. That there. There we go. Okay. Actually, I'm going to move this down a little bit. All right, something went wrong with that one. Let's get rid of him and let's draw in another axis here. Yeah, that's good enough. All right. So the new system, right? The new method, shell method, right? I'm going to go ahead and draw a function here. I'm going to draw, like, let's say that, right? And I still want to do over a to b, right? So same thing happens in the other direction, right? And now we have whatever shape this sort of creates. So dropping that down, dropping that down, dropping this down, dropping this down, right? Hopefully you guys see. This picture might be clearer than the other one. So this is sort of like the shape that I want to find the volume for, right? And then this sort of connects right here like that. And then this is going to be around there. Hopefully you guys see that shape. It's got like a little squiggle on the top of it and it's flat on the bottom, okay? And it's missing that hole from that distance from 0 to A, right? So now I'm going to go ahead and do the same exact construction here, and I'm going to sort of thicken that up a little bit. I have this as the cylinder that I'm going to be playing around with, right? And this one I'm actually going to darken in. I'm going to sort of add some squiggles in here, right? And then it's going to be, let's do that a little nicer, yeah? And I'm going to go ahead and do, there we go. I'm going to grab that, give it a sort of a thickness, and then there we go. Swing out a little too wide there. There we go. You guys see that? I have a feeling this is much better than the picture that I provided up above. There we go. There's our nice little cylinder if you guys make believe good enough. There we go. Okay. We have our cylinder there. Hopefully you guys see it. It's that darker blue sort of soda can that's right in between everything, really. Okay. So let me highlight the things that we want to take a look at, right? So remember how I said it's from A to B. So it's this region that's right here that we're trying to revolve around the y-axis, right? Does that make sense? This is the region that we're trying to revolve around the y-axis. That'll give us our outside shape, right? And the way that we find the volume of that thing as we revolve it around is that thick blue sort of soda can that you guys see in the middle there, okay? When we revolve that around the y-axis, that has a volume. If we take all of those volumes, add them all together, we get the total volume, right? And that's what gets us the volume, a good approximation for the volume of a shape itself, right? Okay, so now let's go ahead and dissect this a little bit, right? So if you guys remember, I gave this a thickness. If you guys remember, that thickness right there, right, was going to be my delta x, right? Which ends up turning into my dx, right? Notice that there's a height that's attached to it. So this height right here, right, that is dictated by my f of x, by my function itself. I forgot to write in the function here. So let me actually draw it in purple so it stands out a little bit. No, yeah, purple. I'm running out of colors. There we go. So that right there is my f of x. So the height is dictated by that f of x, right? And the one thing that is sort of missing, right, is sort of a radius. How far out did we have to go, right? How far out did we have to go to get to my soda can, to get to my one little soda can, right? So that was going to be my r, right? And that radius is dictated by x. So then that means, right, that the area of this cylindrical shell, okay, if we sort of sliced it down one of the edges and just completely unwrapped it, right, the volume for that soda can, the volume for that soda can was going to be 2 pi r. Let me write that a little smaller, actually. V 2 pi r, right, times a height. times my delta x, right? And if we do it for this particular one, right, we have v is 2 pi, my r is x, that's how far out we went, times h, my height, which is dictated by the f of x, and that turns into times dx. That's where we get this statement up here. And there you have it. There's all three of the methods for Calc 2 for how to find a volume, okay? The first one, the first two, right? And hopefully you guys see that they're fairly simple, right? They're fairly simple to sort of pick out, right? The third one, the shell method, that's the one that's a little bit harder to sort of dissect, right? But it's all there, right? It's not too much more than some basic geometry, okay? And some experience. Cool. Okay. So one thing I do want to mention before we keep going, the integral, I mean, this table that I just made, right? I did it for various functions, right? And all of these were dx. Notice that all of these, right? We were doing it with respect to the x variable, right? There's a similar table, right? If we want to do stuff with respect to the y variable, if you want to do stuff dy, okay? And the pictures all sort of fall about just like these, okay? The only difference is instead of going, you know, up and down or left to right, you switch them. That's it, okay? But the one thing I do want to mention here, right, is this phrase down here that, you know, even though the table is helpful, right, there is no substitute. Really, there is no substitute to drawing or sketching the shape as best you can for your computational process, okay? Don't skimp on the detail that you can provide for your drawing, okay? Don't skimp out on the exactness, right? Try to be as meticulous as possible. I can't stress this enough. This is a very helpful skill to have, not only for these couple of sections, right? But later when you get into Calc 3 and linear algebra in our Math 250 course, okay? Be very meticulous with your drawing, okay? Don't skip out on the detail. Okay, so now, I want to do one example for everybody.
So for this example, what I want to do is we're going to solve this integral out. We're going to find this volume, okay? And what I want to point out from the get-go, right, is the fact that sometimes, right, one method might be better than another, okay? And this is going to be clear, I think. This is going to be pretty clear with this one example, okay? So for this section, we've been learning shell method, okay? But what you guys are going to see, right, hopefully, is that even though I could do it by shell method is not the best way to do it, okay? So for this one, we have to find the volume of this function, right, over these two x values, right, on the x-axis, rotated over the x-axis, okay? So I provide a little graph there for everybody to check out, right? So hopefully you guys see what's going to go down, right? Here's the 0 to 2, from here to here. So we are trying to find this region. I'm going to highlight it real nice. This region right here, all of this, right? We're going to spin all of this around the x-axis, okay? Now, I'm going to go ahead and draw my picture for it so I can show you guys what this sort of shape looks like, right? Okay. I'm going to draw the blue in like so, right? I'm going to draw this in like so. There we go. The bottom one can be a little better. Kind of looks like a little Hershey's Kiss, right, on its side. All right. So hopefully you guys see what this is looking like, right? And I'm going to go ahead and put my tick marks in. This is going to be maybe This right here is going to be 1, right? And this over here is going to be 2, right? We need all the way out to here, okay? So hopefully you guys see what the shape is looking like. I'm going to try my very best to sort of draw the three-dimensional Hershey's Kiss on its side, right? And we didn't start very well. Let's try it again. So here's the bottom of our Hershey's Kiss, right? And here's the top. Let me add that little tick mark again. Bam. Okay. Hopefully you guys see the volume that we're trying to find here, right? And hopefully the other thing that I want you guys to look at this point, right, is the fact that if we do this using the disk method, right, super simple, super easy. I'm pretty sure everybody, for the most part, right, has the math going down in their brains already, what to do for disk method, right? Okay. But for kicks and giggles, let's go ahead and do it by shell method. We're going to do the cylindrical shells. Okay. So I'm going to go ahead and I'm going to thicken up my pen a little bit so I can draw one of these representative soda cans, right? Bam. Right. And then I'm going to try to do the same thing over here. Right. Okay. I'm going to whoosh, whoosh. There we go. Okay. Hopefully you guys see the soda can, right? It's sideways. Okay. Most importantly, right, what I want everybody to see is that our soda can, it's got a thickness. I'm going to actually do the thickness right here. I'm going to do the thickness right here. And this thickness is being given by a dy. Got it? Okay. So you guys see how this is going to get a little funky here, right? Okay. So if we're going to do things dy, this is not set up right. Our function itself is not set up correctly in order for us to do an integral along the dy, right? So we've got to change everything now so that we do have everything along dy, right? So then the first thing we've got to do is we got to modify this so that we can get everything in terms of y. Okay. To do that, 1 over x squared plus 1. We can do this, right? Y is equal to that thing, right? A little bit of math. X squared plus 1 is equal to 1 over y. We do it some more, and we get x is equal to the square root of 1 minus y over y. And I should extend that square root all the way down to the bottom. There we go. Okay. So this function, our f of x, right, can also be written in terms of y in this manner right here. So this is the equivalent function that we need, right, but in terms of y. Okay. Next thing. You guys see this thing? Our interval from 0 to 2, that was on the x-axis. If I want to do dy, then I need my limits of integration to go on the y-axis. So this is going to be a little trippy because our function is defined, right, from here to here. Let me do it in a nice flamboyant color so people can see from there to there, right? Okay? So now we have to figure out what our limits of integration along the y-axis are, right? And this is going to just take into account from here, whatever this is, to 1. You guys see that? We still have to add in sort of like the little hole that's going to be sort of like the cylinder. How do you guys see that? There's going to be a cylinder in there that we have to also take into account, right? Okay? All right. So how do we find these limits of integration? We have the function itself, right? we know that x goes from 0 to 2, so now we have to find the equivalent limits of integration, right? But along the y-axis, right? So when x is 0, right, then y is equal to 1 over 0 squared plus 1. Let me just go ahead and keep going in terms of an equal sign. This thing ever erases. There we go. Is equal to 1 over 1, which is equal to 1. So one of our limits of integration is y equal 1. Make sense? If x is equal to 2, right, we do it again. Y is equal to 1 over 2 squared plus 1 is equal to 1/5. Does that make sense? So what we just did is this. We basically said 0 to 2, right, on x-axis is equivalent, right, and let me put my bars here, is equivalent to 1/5, comma 1 on the y-axis. Got it? Okay. So we have our function, and we now have our new limits of integration. At this point, we can just go ahead and throw it into the cylinder method, right, based over dy, right? And we can go ahead and crank out a volume, okay? So the equation for it will go like this, right? The volume, volume, right, is going to be equal to the integral, okay, from 1/5 to 1, okay, of 2 pi y times, right, times my g of y. Okay, and that's going to be integral 1/5 to 1, 2 pi y times that newfangled square root 1 that we have up there, right? Okay, 1 minus y all over y dy. In terms of the calculus, this is it. This is what we need to solve. Okay, I'm going to simplify it. I'm going to write the 1/5 a little nicer. I'm going to simplify it a little more, right? Equal to the integral from 1/5 to 1, 2 pi times the square root. This is a bunch of pre-calc to get this right. If you don't entirely see it, write it out. Take the time for it, right? Okay, there we go. This is what it's all reduced down to, at least the nicest way that we can write it down. Okay? Okay. There is a problem, though. There is a big problem here. Okay? This right here, this is the integral that we need to solve in order to get at least part of the volume. Okay? Because if you take a look, right, from 1/5 to 1, you guys see the limits of integration, right? From 1/5 to 1, that is basically from here to here, right? That is just all of this. Whoa. There we go. Well, let me go back there. Yeah, that's all of that, right? It's missing that middle core portion from 0 to 1/5. So we have to add that eventually anyway, right? Because otherwise we won't have the full volume. We're just going to have sort of like the volume of the Hershey's Kiss with that middle core missing, right? Okay? And it turns out, and I'm going to write this down here, this integral right here, using the current methods that we have at our disposal up to now, we can't solve it. So I'm going to write that down. Not We cannot solve this integral using current learned methods. Okay, we actually need to go to trigonometric substitution in order to solve this, and we learned that in chapter 3. So we're not there yet. Okay, so I'm not even going to compute this. I'm going to leave it there. Okay, you can go ahead and grab the integral calculator and type this in. It'll give you an integral. Yeah. You do have to add this portion right here. You do have to add, remember, it's missing the cylinder in the middle. It's missing the core of the Hershey's Kiss, right? So you still have to add this in order to get the full integral. Whoa. In order to get the full volume, okay? So it's still missing something, even if you can compute this, okay? But what I want to point out, right, is this, that for this problem, okay, and this is generally indicative across all of these integrals that you might be able to run into, right? One method might be better than the other. You're not required to do one or another if you see something better or easier, right? Depending on what you draw, okay? In this case, right, like I said, you're able to do this problem. You're able to find this volume much easier, much easier if you do it disk method, okay? But like I said, for kicks and giggles, right, we did it using shell method. This is completely correct. All of this is completely, everything sort of flows, right? The equations make sense, the construction makes sense, but doing it cylindrical method is much harder. Much harder. You're taking into account, you have to keep track of much more stuff, and you have to modify everything, right? So when you do these problems, right, it is up to you to decide what method you want to do, okay? And that's what's going to come in the quick checks that are going to follow right after this, okay?
And that's exactly what I want you guys to try out in these next two examples. So quick check 2, I'm going to have you guys do odds and evens, okay? These two are shapes that I want you guys to choose just any, try to find the volume, right, for these shapes, but use whatever method you want, okay? What I want everybody to do in particular for this first one, right, do non-cylindrical method. So non-cylinder. Okay, try to do this without using the cylinder method. Okay, so washer method, disk method, use one of the other methods to find this shape, the volume for this shape. Okay, and what I want everybody to do after that, quick check 3, now I want you to do it using cylinder method. Okay, it's the same. For both of these, you should get the same answer. You should get the same answer. Okay, one you'll see is much difficult than the other. Okay, and they're not always matching in terms of difficulty. So in one of these, cylinder method is much simpler, right? And in one of these, the disk method is much simpler. So keep that in mind. Okay, but I want you to try out both methods. Okay. So moving on, okay, there's one type of volume that I haven't shown you guys yet, and that's when it's sort of offset, when the center is not sort of one of the X or the Y axes, okay? So, and that's the one that I want to cover with this one right here. So I want to sketch the region bounded by the given curve, right? And find the volume of the solid that's obtained by rotating the region about that specified line. And I want to use specifically the shell method to do it, okay? So the function that I'm going to do is this one right here. F of x is equal to x minus 1 plus 1 from 0 to 1. And I'm going to rotate it about the line x equal negative 2. Okay, so I am going to, let me first of all draw this shape out so you guys can see what I'm talking about. My x equal negative 2 line, that's this. Okay, I have my sort of my curve. I see my f of x, that's this thing, right? And I want it from 0 to 1. So I'm going to go ahead and sort of slice this down here, slice this down here, so I can see my region. This is the region that I want to, this is the region that I want to, this is the region that I'm talking about, right? This is the region that the problem is talking about. Okay. And I want to revolve this. I want to revolve this region right here about the line y equal negative 2. I want to do this. I'm going to spin it this way. Okay. So let me go ahead and scroll down a little bit. Let me zoom out a little bit because I need to slap down some x and y axes. I'm going to do black line. There we go. And I'm going to go ahead and do another one right here. I'm going to bring this up a little bit so I can have a little bit of space right below it so I can add the depth that I need. Okay. Now, here comes the toughie part. Trying to draw this shape. Okay. So if you sort of think about it, right, we're trying to, the middle line, the thing that the center is our x equal 2 line, right? That dotted red line that we have there. I want to revolve this around that line. So the other end of my shape is going to be at around x equal 4. So I'm going to go ahead and do 1, 2, 3, 4. So this is my 4. This is my 2. Right? I'm trying here. I think I need to make them a little better spaced apart. So 1, 2, 3, 4. Here's my 2. Here's my 4. Okay. That red line is this right here. Okay. My region, let me scooch that over a little bit. It's halfway. My region is this bit. So I'm going to go ahead and do to 2. So 1, 2, 1. My region is this strip right here. It's going to go boom right there. And I'm going to go ahead and shade it in just like I have it above. Just so we can match up the shapes. All right, here comes the fun part. This exact same shape is going to be on the other end. So it's going to go up to here about, and all the way up to here. My shape is going to go like that. I think that went too high. About to there, right? So these two are exactly the same region, sort of like mirrored, mirrored, shapes. You guys can take a look at that. You guys can see it, right? And I want to revolve it around that line y equal, or x equal 2, right? So here we go. Here's my shape. So there's going to be I'm going to draw a dotted line here, dotted line there. Going to be a something like that. And then there's going to be sometimes these pictures become much easier or much clearer because of the shape itself. So let me draw in the side walls. There you go. Hopefully you guys see what this is looking like. This is looking like sort of, picture like a little chalice that's in between, right? And that chalicey area is just empty. Okay? There is our shape. There is our shape. Okay? So now, hopefully you guys see the cylinders, right? I'm going to go ahead and draw in the cylinders here so it becomes a little clear what I'm really going to be looking at, right? I'm going to draw a nice little thickness, and then I'm going to drop this down so I have, there we go. And same spot on the other side, and I'm going to drop this down here. Like I said, you don't have to be precise, but be as meticulous for yourselves as possible, right? Be as meticulous as you can be. Be as meticulous as you can be. I'm going to thicken up the line a little bit. Maybe I can. Yeah, there we go. There we are. And then the last lip that goes sort of across here. There we go. Hopefully you guys see our little soda can there. So that's the soda can. That's the random soda can that we're going to be using, right? To sort of give us all of the numbers, all the things to formulate our integral, right? Okay. So if you take a look, right, this soda can has a height. It has some height. And that height is dictated by my f of x. If you guys notice, if you guys remember, right? Remember that this right here, too thick. This right here is dictating my height right here, which is f of x, right? Okay. So this is my f of x here. Okay. We have a thickness. Notice that the thickness of this cylinder, right, is my delta x, right? That's going to end up turning into my dx, right? So all that's left now, here's the tricky part, okay, that we want this distance right here because we need that radius that goes outward. We need that thickness, right? We need that distance, okay? And that distance, right? And actually, I'm going to go the other way. The other way is a little clearer to see when you go out this way. That distance right here is going to be my radius, right? And it's going to be 2 minus x. That is going to be my radius, okay? So now, this is where I don't want to say deviate from our formulation of the cylinder, right? But we're going to step back and we're going to do this version of it, 2 pi times r times h times delta x. We have to step back to this one, okay? And this is what we need to do if we get these offset rotations. So notice how this one was based off of this line, x equal minus 2, right? We were rotating it around x equal minus 2. Because of that sort of offset from the x or the y axis, we got to do it this way, okay? So that's the reason why we have a good picture. Let's go ahead and combine everything to make sure that everything fits in here, right? We know what r is. That's going to be r2 minus x. My height is given by my function, right? So it's going to be times x minus 1 quantity squared plus 1. And my delta x becomes my dx. Okay. Now, the strip that we are concerned with, right, our limits of integration are still going to be from here to here, and that's going to be from 0 to 1. So we have enough now to combine everything and get our answer. This is going to be the integral from 0 to 1 of this thing right here. 2 pi 2 minus x minus 1 quantity squared plus 1 dx. Okay. I'm going to expand this little bit right here. So you guys can solve this however you need to. I'm going to go ahead and expand like how I see it, how I like to do it. 2 pi 2 minus x. X minus 1 squared plus 1. That's going to be x squared minus 2x plus 2. Okay. And if you expand this all out, right, integral from 0 to 1, 2 pi minus x to the third plus 4x squared minus 6x plus 4 dx. Since I'm still doing this, right, with respect to the x variable. Okay, this integral now becomes 2 pi. I'm going to go ahead and do the integral now. Minus x to the fourth over 4 plus 4x cubed over 3 minus 6x squared over 2. I'm going to put that in parentheses, that one too. Plus 4x evaluated from 0 to 1. Okay. If you do the math, you do the algebra for it, you're going to get 2 pi times 25 over 12 if you do the common denominators and all that stuff. And this should be 13.08 and change, ... Okay. Now, just for kicks and giggles, just to make sure that we did everything correctly, I'm going to go ahead and double check my answer with our definite integral calculator. Okay, so we know what the integral's got to be, right? Let me go ahead, go back. And I'm going to go ahead and type in this one. I'm going to go ahead and type in this version right here. Okay. So I'm going to go ahead and open up my Desmos calculator. There we go. 2 pi 2 minus x squared minus 2x plus 2. And I still want it from 0 to 1. There we go, 13.08. We're good. Okay. So the last bit for this section. I keep on bringing up the fact that, you know, well, I hate when my computer does that. There we go. I keep on bringing up this fact that, you know, in Calc 3, and in Calc 2, at the very beginning end of this you know, finding volumes here, I keep on bringing up this fact that you have to get good at drawing. You have to get comfortable with at least drawing something, right? Draw your shape. It'll help organize your thoughts. It'll help organize your math. It'll help pick out, you know, any discrepancies that you have, right? But always the question comes along, two questions that come along. Which method do you use, right? And the other one is, well, how do I know if I'm drawing my shape correctly? Okay. the answer to both of those is experience. So you just got to try them out, as many as you can. Okay. That goes for both questions. Which method is best, and how do I know if I'm sketching this correctly? Okay, just experience. Okay. As I pointed out before, you can use any one of the methods to solve for the volume of a shape. You can use any of the methods. Okay. Now, the other thing that I want to sort of provide at least some direction for is, how do I know if I'm sketching my shape correctly? Unfortunately, there's not very many 3D calculators out there that will actually do the calculation for you, right? There are a couple that will at least provide you something that may give you a shape. Okay, it still requires your verification, right? It still requires you to at least be able to picture it in your mind, right? Um, there isn't one good spot for a 3D calculator or a 3D visualization for any one of these shapes, unfortunately. Okay. I do have, though, some honorable mentions, and I've written them down here. Okay. As a basic graphing calculator, Desmos does perfectly well, right? And then I have three more from below that. There's Wolfram Alpha's Solids of Revolution. I put that I put the web page for them there. Uh, there's another website, math4u.net. They have their own, okay? And then GeoGebra has the Solids of Revolution's grapher as well, okay? Um, none of these three, uh, there are some of these three that will do some of the volumes that I've been showing you guys, and then some of the other ones, it won't. Okay. I don't want to say a hit and miss, right? Uh, but it's not sort of it's not your golden dagger here. Okay. It's not none of these will be the one size fits all. Uh, in any case, right? Just make sure that you're able to visualize this shape. It still requires your sort of identification, and you're sort of thinking about it to make sure it's the right one. Okay. Uh, If you use any of these websites, I highly recommend that you use this on something that has a bigger screen. I would uh, I would want to say no phones and no tablets. I don't think the tablets or your phone have processors strong enough to be able to sort of handle the 3D-ness of it. Okay, you're going to need something that has, a sort of like a bona fide processor. One of the maybe a higher end tablet, um, or a flat out laptop or desktop computer. Okay. Um, I know that this is a PDF for the notes, right? So if you go over to the right here, I've got the same sort of spots, same sort of websites here at the edge. So if you look at this on a computer screen, you'll still be able to click on them. Okay, you don't have to sit there and type this into a web page, okay, or type it into the browser. Okay, all right. I know this is going to be a tough section for a lot of people. Okay. Um, Try it. I have my office hours. I have my Friday hours. Please come visit me. Okay. And I am checking my emails fairly regularly. Okay. Besides that, I'm all done for this section. Happy studying.